Okay, directly come to the slide now. So last topic we are discussing about the total acceleration. That is the most important thing. It will come several times in your next topic. So again, I'm just one slight repetition of this part. So material derivative portion. Why I am again and again telling, because it is the most important thing. So that is the total acceleration component. Total acceleration component is d by dt of, that is a total acceleration. So it having two parts. One part is dv dt, temporal component. Another part is v dot del as a set. This is an advective component. It's known as the advective acceleration. First part known as the local acceleration or temporal acceleration, or somewhere it is called temporal acceleration. Is the two part. So material derivative is this one, d by dt is the material derivative or substantial derivative or total derivative. This total derivative, two part, partial differentiation part, another is the spatial. It is a Cartesian coordinate. Whatever we are telling, it is a Cartesian coordinate. But whenever we are writing in the vector form, whenever we are writing in the terms of the vector form, but this is most general. It is the most general form. So if you change the coordinate, Cartesian to polar coordinate, or you come to the cylindrical polar coordinate, so this equation will not change. In the form of the vector, whatever writing, this equation will not change. Because cylindrical polar coordinate, you know, the velocity vector is nothing but the velocity radial into radial direction plus velocity tangential into tangential direction plus velocity jet into. So this will not never change. This thing will not change. In that case, the delta also cylindrical polar coordinate, that is also delta is nothing but I into I, better to write it I know, ER into d by dr. Radial direction, tangential direction. E theta is equal to d by r d theta. Ez. The basic equation will be changed. So v dot del, whatever you, that time it will, some changes will come. But this is most general cases. That's why we use this thing. It's the most general cases. Whether you change the coordinate, this will never change. But this material derivative concept, material, the second portion might be changes with the coordinate to coordinate. Because the Cartesian coordinate, the velocity, and that is the u, v, w. But in polar coordinate, it is not the velocity. A different velocity is there. But this is the most general cases. That's why I am taking it in terms of the vector form. So if you are given the velocity component and del, you will easily can find it. So that's all. Next thing is the important thing. It is very difficult to map the velocity vector in the flow field. It is very difficult to, because the velocity vector here for the flow, if you're talking about the flow field, over the flow field, it is very difficult to get the velocity. So to map a velocity vector, to map the components of velocity vector. What are the components in Cartesian coordinate? U, V, and W. These Cartesian components, to map the components of velocity in the flow field. Is very difficult. Thus, you have to invoke one concept of imaginary lines. You have to take one concept of imaginary lines concept, line concept. You have to invoke this concept in qualitatively and quantitatively. That is a good concept. Some imaginary line you have to consider over the flow field. That is the cases. Sometimes in statistical sense you can trace the vector. Some statistical, you take the photo of this part. You got the displacement, you got the velocity. So to get the flow field velocity, one analysis is the PIV. Particle image velocity. Particle image velocity. Where you are visualize for the study purpose or research purpose in the particle image velocimetry, through which we are getting the flow field on the sense of the statistical sense. You get, and then post processing the velocity. But most important case is here, the imaginary line concept is under your scope here. I'm not going to discuss about the PIV machines, the optical one method to visualize the flow. Here, according to the Stokes number, I'm not going that much detail. Now we'll see the imaginary line concept, why it is coming, because to get the velocity vector. Importance is that to get the velocity vector. If you don't get the velocity vector, how will you get the acceleration? It's not possible. So that is why. So imaginary line concept is coming. So imaginary line concept, 3 imaginary lines we are considering here. First thing we'll see the streamline. First thing we'll see streamline. So definition of the streamline is such an imaginary line you are considering in the flow field at any instant of time. So first of all, at any instant of time. First you fix one time, some time, at any time. At an instant of time, you consider one imaginary line over the flow field in such a way. You consider some imaginary line in such a way on the flow field that if you draw a tangential over the line, if you draw a tangent, any point, if you take it in this point, you take in some point A. If you draw a tangent from the point, this will give the direction of the velocity. This will give the direction of the velocity. That is the definition of the streamline. So what I am telling, I am repeating, streamline can be defined as the streamline is an imaginary line. Is an imaginary line drawn in the flow field. So imaginary line drawn in the flow field. If you draw a tangent at any point, on the line, it will give the direction of the velocity at the same point. It will gives the direction of the velocity at the same point. But at any instant of time. That is the most important thing. So point A, there is if you take another point, point B. So if you draw a tangent, the velocity direction in this side. So each and every point, if you draw a tangent, this will give the velocity of the particular point at this instant. This concept is coming as the streamline concept. So what is the importance of the streamline? Because streamline, what is taken? For this instant, the velocity having only one direction. So flow can be taken as the one-dimensional flow in terms of the one-dimensional flow. At this instant, so it is a local condition type. The streamline concept is coming in this way. So that is a beyond to take that streamline concept. So for an instant of the time, it is a like the one-dimensional type. Now the streamline equation, we are going to see the streamline equation first of all. The streamline equation, now I am coming here. If you consider one streamline, imaginary line over the flow field. Now in between, 2 points you take, P1 and P2. Over here, 2 points you take. Now at P, the velocity vector is the tangential. Tangential vector is the velocity vector. So V is the velocity vector, which is nothing but Ui, Vj, Wk. At point P1. At point P1. We are taking another point P2 nearby. So P1, P2 nearby we are taking. That is the delta R. That is the delta R. This vector is a delta R vector. Okay. So P1 to P2, one more vector is a delta R vector. Position vector from P1 to P2 we are taking. Now here, if P1 and P2 is very close, if P1 and P2 is very close point, limiting value. So this we can write it down dr, very small differential, very small is, and dr, the position vector, this can be written as the I dx plus y dy plus k dz. Very close to point. Now here, what is telling? So dr vector is in this side. P1 and P2 is just trying to closing as much as possible in such a situation. So hence what you see, the dr vector and v vector direction, the direction of both vectors are same. Because as you keep P1 and P2 point very closer, so it is trying to come tangential in nature. That is the concept of the tangential. So the angle between them are 0 degree. Angle between them 0 degree. Hence we can say dr cross v cross product is equal to 0. The vector, that is the sense of the vector is most important in this chapter, because the cross product, then cross product concept is correct. If you forget, I just recap you in the how to do this kind of the operation. So is a null vector. dr cross v is equal to null vector, as both are in same direction. Theta, angle between these two vector is 0 degree. Because sine component, sine 0 is 0. That's right. So what is that? If you forget that I'm doing it, you just check. dr cross v, we can write it I, j, and k. So first dr, there is dx, dy, dz. dx, dy, dz. Next v, u, v, w is equal to 0. U, v, w is equal to 0. So hence you go for the operation. What is that? So what is coming? So I into this 2. So I into omega dy minus v dz minus v plus k into u dz minus omega dx. U dz minus omega dx plus k into v dx minus u dy is equal to 0. That means all are 0. So omega dy is equal to v dz 0. We can say u dz is equal to w dx. We can be able to say v dx is equal to u dy. What does it mean? It means that dx by u is equal to dy by v. Here, same dx by u is equal to dz by. So dz. This equation is the popular equation is known as the streamline equation. This equation is known as the streamline. We are getting by this. We are getting this thing in this manner. So null vector concept we are taking here. Null vector means so 0 magnitude along I direction, 0 magnitude along j direction, 0 magnitude along k direction. So I am writing it down in the fresh way. The streamline equation, most important thing, streamline equation. We are getting dx by u, dy by v, dz by. That is a streamline equation. From which concept we are getting? The concept we are getting it. If you forget any time, you can solve it. dr cross v, position vector and velocity vector is a null vector. Cross product of these two is a null vector. It tells that both are in same direction. So dr position vector and v are in same direction. That concept brings, we verify this thing that over the streamline, at any point, if you draw a tangent, this will gives you the velocity at that point, at the corresponding point, at any instant of time, at an instant of time. That is the concept of the first imaginary line is known as the streamline. Streamline is very, very important concept we are talking about here. Next concept we'll see here, that is the streakline and pathline. Before to telling about the streakline, I am going to the pathline. Pathline is just a Lagrangian concept. What is the Lagrangian concept? Particle tracking system. If you trace one particle, a particle was at here at t is equal to 0 time. After t is equal to 1 second, particle is at here. T is equal to 2 second, particle is at here. T is equal to 3 second, particle is at here. So you are tracking the particle. So if you draw a line between all the times, this line is known as the path line. Locus of a particle. If you are tracking a particle, the locus of one point at corresponding time will gives you the line is known as the path line. It's known as the path line. What is the basic difference between path line and streamline? We come back to the streamline again. The streamlines are parallel in nature. How? Better to write it, the streamline, two streamline cannot intersect. Because if you say that two streamline is intersecting at a point, two streamline intersecting at a point, at any point. So this point, the streamline 1, the streamline 2, both are intersecting. Let you take, assume. So about the streamline 1, the velocity component is in this side, in this direction. And about here, the velocity is. So one point having two different velocity direction is not possible. So two streamline cannot intersect each other. A single streamline cannot cut each other in this way. It is also not possible. A single streamline cannot be like this. Because the cutting point again is a cutting point here. Again, you will get the two different velocity direction. That is concept is not possible. So importantly, I'm telling the two streamline cannot intersect. A single streamline cannot cut each other. But in case of the path line, as a single particle, they can intersect, they can cut each other. Because path line is the locus of an individual particle. Locus of an individual particle. Okay. This is the concept of the streamline and path line. Now you see the streak line is the most important. Why it is? Because to visualize the flow, the streak line is most important. It is using for the to visualize the flow. Tie one tie engine over it, and you want to see the what the movement is there. Streak line is important. So what is the definition of a streak line? It is also another imaginary line. It is the locus of at any instant of time. First, at time t1. Let you take at time t1. Time t1. We just take one snapshot at a corresponding time. We want to take one snapshot at a corresponding time. What we see here, one particle is at here, 2, 3 particles. Particle 1, particle 2, particle 3. That is the location of 3 particles. At time t1. Okay. These 3 particles, all particles had passed through a common point previous at prior instant of time, at prior any time. So let you take this A particle that is some common point. That common point. All particles is a locus of the particles at any instant of time. The imaginary line locus of the particles at number of particles is a locus of the number of particles which had passed through a common point any prior instant of time. So maybe any prior time, some time, let you take, we are taking the snapshot at some second. Some snapshot, we are taking just a snapshot of this thing. And if you join these 3 lines, it is the streak line. This line is this imaginary line is known as the streak line. Why we can say it is a streak line? Because the particle 1 passed through this point, particle 2 also passed through this point, and particle 3 also passed through the same point. All points, point 1, point 2, particle 1, particle 2, particle 3, previously at any time, let it be the different time. At t is equal to 1 second, particle 1 passed through the line. t is equal to 2 seconds. For the example, at t is equal to 2 seconds, particle 2 passed this point. At t is equal to 3 seconds, particle 3 passed this point, common point. But they have passed the common point, passed through the common point, and we are taking here at t is equal to 5 seconds, the snapshot. T is equal to 5 seconds, we are taking the snapshot. And what we see? The locus of the points, locus of the particles. This concept is coming as the Streakline concept. Here, the initial time, you see, initial time may be variable. The initial time is variable. Is variable. Particle 1, some different time it passed through. Particle 2, some different time it passed through the common point. Particle 3, some different time of the, and now itself some particle is at here. At t is equal to 5 also some particle is at here. That is the condition. So that is the condition in. So this line will gives you the Streakline concept. So Streakline is an imaginary line of the particles at any instant of the time, which had passed through a common point at any prior instant of time. That is the definition of the Streakline. So better to understand, when the all three lines are identical, at the steady condition, at steady state, the most important thing is at steady state, flow is the steady flow. Such a situation at steady state, steady flow condition, or the better to write it at steady flow, because we have already discussed about steady flow. At steady flow, the streamline, pathline, and streakline all are identical. You cannot distinguish it. At a steady flow, you cannot distinguish it. All are identical in nature. So that is the concept of the imaginary lines. We are telling why we invoke the imaginary line concept, because to map the velocity vector in the flow field, we have to know the velocity vector. That's why we are getting this thing. Streakline, importance of the streakline to visualize the flow. Definition of the streakline is most important. I am telling again and again, because if you're not understanding, it is the imaginary line drawn in the flow field in such a way the locus of all points which has passed through a common point at any prior instant of time. That is a streakline. Pathline is a simple thing, locus of an individual particle is a pathline. In streamline, imaginary line, you are considering in such a way that at any point, if you draw a tangent, it will give the velocity vector of the corresponding point at any instant of time. Streamline cannot intersect, two streamline cannot intersect, one streamline cannot cut. That's the concept we are giving here. One problem would be the best thing to get this streamline, streakline condition. So I'm just going to solve slightly. I'll give you the clue how to do this. So U is given as the AX into 1 plus 2. With the X to the velocity at along X. The velocity along V, Y is given, V is equal to P1. And W is equal to 0 means it is a no velocity along Z axis, so it is a two-dimensional case. So two-dimensional case means du dy, right? Dx du by dy by v. The streamline equation. Simple streamline equation we are writing it. Third term will not come here. So dx, just we put this thing. 1 plus 2t dy that is the thing we are getting it here. Next, the remaining task is simple. If you go for the integration of this equation, and you will get the equation, this equation will gives you the streamline equation. This equation will gives you the streamline equation. Simple. Remaining task, because this will be come out of the integration. So 1a into 2t will come out of the integration, and it will come as the ln x is equal to 1 by v and y. This way you are getting this equation of the streamline equation. You solve it integration and getting it. Simple thing it is. Simply just write it down the streamline equation, put the u and v values here. Same way, if you asked the Streakline equation of the Streakline equation, what I'm telling you, in the Streakline equation or Pathline equation, when you write it down, u is given as the ax into 1 plus. You see, the Streakline and Pathline is a Lagrangian concept because you are tracking the particles, fluid particles. So as it is a Lagrangian concept, so u, the Lagrangian concept, you can write it u is equal to dx dt, v is equal to dy dt. If w is present, w is equal to dz dt. The Lagrangian concept you can write it down. But Eulerian concept you cannot write in this way. So dx by dt is equal to ax plus 1 by 2. Okay. So dx by x into a into 1 plus 2t what should be the limit of this integration? That is the most important thing I'm going to tell you. In the case of the Streakline, if you know the definition of the Streakline, the limit will be some time there mentioned t is equal to t1. So final is the t1. Okay. So here 0 to x, let you take 0 to x or some point to x. x0 you can take or some initial common point, because all points is coming through a common points. So common point is the lower limit. So let you take the common point is at x0. x0 is the common point at lower limit. At what time it is passed? Let you take some particle passed at here ti, some initial time is equal to t1. If you do the integration, what will be happen? ln x by x0 a is, you put it here, so t1 minus ti plus t1 square minus ti square. So here the ti is unknown. Which time? Ti. That is the equation number 1 you are getting. Here dy by same way dy dt is equal to by. You write it down, this equation from here. So dy by y into d into dt. So hence again integration. So y0 common point by the final at T is equal to T1, what is the location? Here, Ti time is a T1 time. So ln y by y0 b Ti minus T1 minus Ti. So from here, this Ti, if you replace the Ti value, you will get the equation. This equation is nothing but the Streakline equation. So the lower limit is is unknown. So you get the Ti value from this equation, equation number 2. You get the Ti value and replace it here. Replace in the equation 1. Whatever the equation you will get, that is the Streakline equation. Concept is at here. Streakline the lower limit. Now Pathline equation we are getting. Pathline equation and Streakline is the similar manner we will do it. Now Pathline equation is the same way. U is equal to du dx dx dt is equal to ax 1 plus. Same manner, dx by t a into 1 plus 2t. Here, integration, pathline concept, initial any point, because pathline is a Lagrangian concept, initial point, final. Initial time, let you take some initial time somewhere else into final. Here initial time, here TF to be removed. TF is unknown. EF is unknown. So two equation, you have to, second equation, from the second equation you will get the TF value and replace the first equation. Same thing is coming, just here upper limit you have to replace, the Streakline cases lower limit you have to replace, because Streakline the any prior instant of the time, that is the variable case. Here final time is a variable for the pathway. That is the difference between the two concepts in here.